Chapter 15 is on multi-objective least squares. This is an extension of least squares. In practice, it turns out we're going to very quickly reduce it to the standard least squares, so we know how to do it, handle it mathematically, but it's very, very useful in practice. So we'll start by saying what the multi-objective least squares problem is. So here's the problem. What we have is we're supposed to choose an n vector x. That's no different from least squares. But the difference is now, instead of having one least squares objective or norm squared objectives, we actually have k of them. So I have, norm a1x minus b1 squared, but all the way up to norm akx minus bk squared. So I have k different things that I want small. Okay. Now here, AI is an mi by n matrix. They can have different numbers of rows, and bi, of course, is an mi vector. And we refer to the ji as the objectives in a multi-objective optimization problem. Another name for that is a multi-criterion problem, because you have k things you care about. The only thing that's absolutely settled is you'd like all of them to be small. So that's the main, that's the only thing you agree about. But we haven't yet said which is more important than the others. That's coming. Okay. Now, of course, in this case, we know how to, if I asked you to minimize J1, you would know how to do that. That's least squares, J2 or J3. Now, what we want, all of them small. So that's how we're gonna, that's what we want to do. That's the job here. Okay, now here we're going to follow a very traditional approach. The traditional approach when you have multiple criteria is to actually add them up. Multi-objectives is you add them up with weights. So we're going to form a master objective called J, and it is going to be a linear combination of the objectives for the k problems. So that's J1 up to Jk. And these weights, lambda 1 through lambda k, they have to be positive. It wouldn't make any sense if they were negative, because that would be an encouragement to you to make that one big. We want all of them small. So this is going to be our so-called weighted sum objective. And some people refer to this as a scalarization of our multi-criterion problem. So our original problem has k different things we care about, J1, J2, up to Jk. What this says is that we're going to scalarize it, and we're going to say we're going to get some weights, and we're going to form a single scalar number j. Okay. Now here I can multiply all these weights by any positive number I like, and nothing would happen. It wouldn't change. It doesn't change the solution. It does change the value of the j's, but it doesn't change the solution. So it's very common to take lambda 1 to be 1. And if it's not 1, I simply divide all of my other weights by lambda 1, and I get a new set of weights where the first one is 1. And in that case, people refer to J1 as the so-called primary objective, right? And usually that's the thing that you really actually care about being small, and the others are things that are more like desiderata, like if possible, please make them small. Okay, and we can interpret the lambdas. It is lambda I is how much you care about Ji relative to the primary objective. So if lambda is 5, it says it irritates me 5 times more for J5 to be large than J1. If it's 0.5, that says it's half. It irritates you half as much. And so these parameters, lambda 1 through lambda k, or they're sometimes called hyperparameters. And they're going to be different, and we're going to see that we're actually going to, in practice, you'll choose different values. We'll see about that momentarily, or in applications. Now, an important special case of this is the so-called bicriterion problem. That's where k equals 2, and that means you have just two things you want small. You want a1x minus b1 norm squared plus lambda times a2x minus b2 squared. And so here, lambda is literally how much the second objective irritates you compared to the primary objective, which is norm a1x minus b1 squared. Okay, now it turns out, now here we just said this is the objective, and now we would say, okay, what we're going to do is we're going to minimize this weighted objective. Now, we could do that. It turns out that we can easily, using some tricks from matrices and vectors, immediately reduce it to a least squares problem, whereupon we know the solution and we don't have to actually rederive anything at all. So here's the way you do it. We're going to write that least squares objective as this. So this is lambda 1 norm a1 x minus b1 squared plus, and then the last one, which is lambda k times norm akx minus bk squared. Okay, so that's j here, and it turns out we can write j this way. Well, why is that? Let's walk through it. This is a stacked vector here, of course. Now, the norm squared of a stacked vector is the sum of the norm squareds of the vectors themselves. That's clear because this is just, well, okay, that's clear. Okay, but the norm squared of, like, for example, this first stacked vector, the lambda comes out, the square root lambda 1 comes out as lambda 1. And so this gives you, this first term gives you exactly that, right? And this last term gives you exactly that. Okay. Now I'm going to write this objective here. I'm going to write it as simply this, as a least squares objective. I'm going to say that J, which is our weighted sum multi-criterion least squares problem objective, I'm going to write it as norm a tilde x minus b tilde, where a tilde and b tilde are these things which are obtained by stacking the original data and applying the square root of the weights, right? So this is a tilde and that's b tilde. So it looks like that. Well, but look, if I walk up down the street and I say, please minimize this, you know how to do that. You've known that for 2 chapters now. You know how to do that. And the solution is just, a tilde transpose a tilde quantity inverse a tilde transpose b, period. That's assuming that the columns of a tilde are linearly independent, which we're going to. So what this means is we've reduced this multi-criterion, this weighted sum minimization problem to a completely standard least squares problem, and we know how to do it. Okay, so you can work it out. I mean, it's good enough just to say it's that, or you could write it this way if you like, a tilde, I should say, a tilde dagger b. It's the same thing, but you can write it out this way, which is actually kind of a beautiful thing. It says, okay, very roughly speaking, the least squares solution is, a transpose A inverse A transpose B. And what this does is it actually basically splits the numerator and denominator. I'm speaking very roughly because these are matrices and vectors, but the numerator is something like this thing here. And you can see it just forms a weighted sum of the numerators, and it says you take a weighted sum of the denominators. Now, it's a matrix, so, but it's, if it's inside an inverse, that's something like a denominator. So that's it. Now, you can calculate this via, QR factorization of a tilde. Lots of ways to solve this problem. Now, an interesting thing is that each of the objectives alone could be wide or have dependent columns. So that we'll see examples of that. Now, of course, when you stack them to form a tilde, that has to have linearly independent columns. But the individual AIs do not have to. Okay. Now, the bicriterion problem, right? Let's take one. We're just going to look at 2 for now. Okay, so we have J1 and J2. We're going to minimize J1 plus lambda J2. Remember that we can always just set the first lambda equal to 1 and call the first objective the primary objective. So we're going to do that here. And then what's going to happen is we're going to imagine that we're going to solve this for many different values of lambda, and we're going to get something called, we're going to call that x hat of lambda. Now that's an n vector, and it's a function of this weight, lambda. Lambda has a very simple interpretation. If lambda is small, it says we really care much more about J1 than J2. If lambda is really big, it means that we really care much more about J2 than J1. And if lambda is 1 or near 1, it means we kind of care about them equally, and so we'd like you to minimize the sum. Now, when you find this point, which is just least squares, we know that's very simple, then these points are what's called, for the bicriterion problem, Pareto optimal. That's named after an Italian mathematician and someone who worked in economics, Pareto. Here's what it says. It says a point x hat or x is Pareto optimal with respect to J1 and J2 if the following. In fact, let me explain it this way. Suppose somebody says, well, I've got an x, and someone says, oh yeah, well, I've got an x too. This is in the context of this bicriterion problem. And then people say, well, whose is better, my x or your x? Let's find out. Well, it depends on the different values of J1 and J2 for the two proposed candidate points, right? So now, if one person, let me write it out. This is J1 and J2, and this is like x and x tilde. There you go. And if this is like 10 and 8, if x tilde comes along and it's 9 and 7, right? Then for sure there's no discussion. X tilde is better. Why? Because you care about two objectives, J1 and J2. And x tilde beats x in both objectives. So no discussion. We don't have to talk about lambdas, nothing. X tilde is simply better, period. Okay, now that changes if this is 11. Okay, now you see this sort of a trade-off. And when someone says, help us, help arbitrate this fight between these two people, one is proposing x, one is x tilde, and we say, well, let's take a look at their objectives. You would say that, okay, well, look, in J1, x tilde beats. It's lower numbered, it's better, okay? But in J2, x is better. So what you would do is you'd say there's a trade-off here. And the fact is, you can't say which is better, x or x tilde. I mean, that's the whole point. So the only thing that's really in multi-criterion, bicriterion, the only thing that's really clear and unambiguous is if my solution has a lower all of the objective values are lower, then I win. That's the only thing that's clear. But if some of mine are worse than some of yours, and some of yours are better than some of mine, then it's like, who knows who's better? You can't say. So now I can tell you what Pareto optimal means. Pareto optimal means it's a point where no other point can beat you. And I'm going to define beating in this context is to mean that it has a smaller value of both objectives. Okay, so and in fact in economics I think they refer to this as dominating, right? So in this case, let me restore this to something that dominates. So in this case you would say here that x tilde dominates x, meaning it's simply better. It's better on both objectives, right? So that means to dominate. And then you'd say a point is Pareto optimal if it is not dominated by any other vector, okay? And what that says is, so here, it's Pareto optimal if there's no point z which beats it in both objectives. And beat means smaller value of ji. Okay, and now when you vary lambda, you're going to get what's called the optimal trade-off curve. You'll get different values of x, and they will have different values of x1, and different values of j1 of x, and also j2 of x, and they'll change. But every single one will be Pareto optimal, and then this maps out what's called the optimal trade-off curve. So we'll look at some examples. So here's an example. We have A1 and A2 are both 10 by 5. B1 and B2 are 10 vectors. And what we're going to do is we vary lambda over, well, this is on a logarithmic scale over a very large range, right? So these are very small lambdas and these are very large. Now, what's happening over here, and this just shows you the value, this is 5 values. This is showing you x hat, okay? So now, for 10 to the minus 4, it says that we really basically care about only J1. So we presume that whatever this is, this solution here, these 5 numbers, correspond to x hat when you only minimize J1, that I assume. Conversely, when I take lambda super big, like 10 to the 4th, that means I really mostly care about J2. I don't even really care about J1, okay? And here you get these other numbers. They're right here, okay? And I presume that is the solution of simply minimizing norm A2x minus B2, okay? So that's it. Now, what's interesting is what happens in the middle. And it's actually super interesting, right? Because I mean, if this was just sort of a line connecting these two, it would not, it wouldn't be that interesting. But what's interesting is that weird stuff happens in the middle. So let's see. I mean, let me just mention a couple of things. I mean, so this is very strange, right? Here's x3, should have the value, I don't know, 0.05 or something in the first thing, and to minimize in the second one, it should be like minus 0.1. What's weird is in the middle, it sort of goes up and then down again. So the point about, and this is a baby example, so the point about this is just not clear at all what's going on here or why, right? I mean, this is it. Here's how they perform. So over here, what we plotted is the same value of lambdas from 10 to the minus 4 to 10 to the 4. And let's see how what that does to J1 of lambda and J2 of lambda. Well, here, J1 of lambda, in fact, for, basically lambda up, as long as lambda is less than around 0.01, J1 of lambda is really small. And presumably that's its minimum value, which is, I don't know, let's call it 6.5. I don't care, right? 6.5. Now, on the other hand, once lambda is big, you're basically minimizing J2. And I assume that the solution of that is whatever that, I don't know what that is. Let's call that 4. Okay, so it's about 4. Okay, so that's that. What's interesting is you can see that in the middle, you get weird stuff. As you move lambda out this way, you're caring more and more about J2 compared to J1. And so what happens is you start doing worse on J1, but you're doing better on J2. It's going down like that. Now, some people plot this in what's called a trade-off curve. This is what people would call a trade-off curve. This is your first objective, right? And this is your second objective here, J2, right? And this is a good way to understand how this works. So I can show you some examples. Anyway, so these are all Pareto optimal point. This is the curve given by the value, the trade-off curve of J1 versus J2 as you vary lambda. And so here it is, and it's kind of cool. And people talk about like the proverbial knee of the curve and stuff like that. So in this plot, being to the left and down is good, because being to the left means you're beating on the primary objective. Down means you're beating on the secondary objective. So this is the idea. These are like these three different specific ones. Actually, you can visualize a lot here. Like for example, if I had a problem and I had this point, this point, this point, and this point, right? And say let's talk about these 4 different choices of x, right? So we can say some interesting things. We could say that this one and this one are dominated, right? Dominated, if you want to know who's better than you, you look at everything that's to the left and below you, because left means you beat on J1, below you means you beat on J2. So we look at this and we can see, look, this point dominates that one. And that means you should never choose that one. I mean, if these are the things you care about. This one is also dominated. It's actually dominated by both of the other two. But these two are neither is dominated. There's no, among the 4 points, there's no point. And so here the idea would be, for example, here, if I made something like this, that's a point we can achieve. You cannot achieve that. That's what's being asserted here. There's no x that would land you in that region. If you did, then this is a big old lie, and that's not the optimal trade-off plot. Okay, so this is the idea, and these ideas have a lot more application than just least squares, and it's something you'll see in a lot of classes, I'm guessing. But it comes up every time there's an optimization problem and you care about more than one thing. You just form a weighted sum and minimize that. Now, the way it's used is you use the weights as knobs to kind of achieve what you really want. So that's the next discussion is, so here's how you would use multi-objective least squares. The first thing you do is you identify the primary objective, like the basic quantity you want to minimize. Like you'd say, I don't know, doesn't matter what it is. This is the main thing I would minimize. Then you choose one or more secondary objectives. And these are sort of things like, if possible, could you make this thing small? Or if possible, could you make my decision today look like yesterday's? Because, it's just that encourages smoothness in the decisions I make, right? Or I would like you to minimize the risk of this portfolio, but I would like you to do it with as few trades as possible. Or something. I mean, with a small trade vector. I should not have said a few trades because that's a different problem. I should have said with a small trade vector. So trade as little as possible to minimize, to also make the risk small. So it'd be things, these are the kinds of things we're talking about. Okay. Now the way this works then is you tweak or tune the weights until you like, or at least can tolerate, x hat of lambda, right? So that's how that works. And the rules are really simple, right? That here, if you think J2 is too big, if you're uncomfortable with it, increase lambda 2. Increase lambda, which is lambda 2. Okay, increase lambda. That says you're putting more weight on that second objective, and when you minimize again, it's going to come out smaller. By the way, J1 is going to come out bigger. So if you think J1 is too big, then you have to decrease lambda, right? Which is the other way to do this, right? And this is how this works. And sometimes this is done in an organized way, but more often than not, it's just done by just fiddling around, literally just like this. You type in a lambda, you'll look at the solution, run some simulation or something to see if you like it. And if you don't, you tweak lambda, and then when you get bored, you quit and you say, that's my x. So this is kind of how it's used in practice. This will be much more clear when we look at some examples, which we'll do next.